So here what has changed with respect to the pure substance is that now our H is a function of not only temperature, but will be a function also of the, well, in general, it will be a function of temperature, pressure, and the quantity of each species which is present in the mixture. So in general, this will be Ni, the number of molecules of each species from 1 to the number of species. So, and what we like to consider here is that if this relation is valid for the difference, for the change of enthalpy, is related to the heat I'm giving to or I'm subtracting from the mixer, if there be something that allows us to make this difference appear also in the in this change of enthalpy. And so in general, if you have no changes of species, as I said, we have just changes of temperature. And on the contrary, if we are considering that there is a chemical reaction, we can assume also that we are providing heat, but we do not change temperature because we are changing composition. So we try to generalize the conservation of energy by continuing to work with our enthalpy for a constant pressure process. And in fact, the reason why there is not this change of temperature, or there can be an exchange of energy without change of temperature, is related to the fact that to rearrange chemical bonds, so creating a species and destroying another one, we have to spend energy, and so, or they release energy. In particular, when we have that this arrangement of chemical bonds release energy, we'll talk about exothermic processes. Whereas if we are considering that we have to spend energy to rearrange chemical bonds and so destroying, creating species, we talk about endothermic process. Exothermic, endothermic. For instance, if we consider that we are standard temperature and pressure, and we have some molecular oxygen, O2, we know that we can consider a dissociation reaction that destroy the molecule of oxygen to get 2 atoms of oxygen. And so we are breaking this chemical bond, and to do that we have to spend energy. So this will be an endothermic reaction that requires energy, and to form these 2 atoms of oxygen, I have to provide heat to the mixture to dissociate. Similarly, if I consider this other reaction, a standard condition, you have carbon in a solid phase and gaseous oxygen in molecular oxygen, standard condition, we can form from these 2 substances, from these 2 species, a molecule of CO2, carbon dioxide, And in this case, we have release of energy. So if this is endothermic reaction, this one is an exothermic reaction. So actually it was this way. So in this case, we have release of energy. Now, in general, this means that if we can obtain this result at constant temperature, provided we provide it in the first case and we subtract it in the second case. So in the first case, I will have our delta Q something over Q, I wrote this in this way before, is greater than 0, because I'm giving energy to the system, and here I'm subtracting energy from the system, so this Q is less than 0. So now we have that initial and final value of enthalpy refer to the same temperature. And so if we look to the first reaction and we use the molar enthalpies, and I consider a single mole of O2, we have that initial enthalpy will be given by a value at this temperature. We have a single mole here and 2 moles of the product of reaction, dissociation product. So here I have a single mole of oxygen and at a given temperature. So, but you know that this value can only be meaningful if compared to a reference value, because we have defined the enthalpy based on this expression. So we can consider that if we select a reference temperature, we have here at the initial condition that are here, we have this enthalpy, and let's say this is better to write this in this way now. Maybe another way, rather than a T reference, we have a reference value of enthalpy. So the eraser is not the best. Let's say that we have a reference value for the O2, and similarly, we have that at the end of the dissociation process, we have created 2 moles of O. And if we have molar reference enthalpy also for the atomic oxygen, we will have to express this in this way. So it's clear that if we select our temperature T as the reference enthalpy for both the molecular and atomic oxygen, we will have HI is equal to 0 and HF equal to 0. So if I say HO2 reference is a reference value that in principle I can select arbitrarily, I say that this is exactly the value that we have at this temperature. Of course, we have HI is equal to 0. And the same if I select our reference value as the one of enthalpy for the atomic oxygen that we have at this temperature, at the temperature we are considering, we have that also HF is equal to 0. So the difference is 0, and this is not compliant with the requirement that to use the enthalpy, we should also be able to evaluate the heat released in chemical reaction. So let's now try to exploit this reference value in such a way that we have uniquely identified, let's say, a unique value of enthalpy, no longer an arbitrary value based on the reference value select, that allow us to include chemical reactions, chemical, let's say, chemical heat release or subtraction in this expression. So we take, we consider the standard conditions as the reference, not as the reference enthalpy, as the reference. And in particular, we define this standard condition as the pressure of 1 bar and as the temperature of 25 degrees Celsius. And in these conditions that we define as standard conditions, we have that the standard conditions for the oxygen is that of molecular gas. So we have O2 gas as the standard condition for the oxygen. So we, considering these expressions here, we can say that our Q should be equal to the difference HF minus HI, so it should be twice. Let's say this is a standard condition, is H0 at this temperature minus the reference value minus the value of HI. So once we have this expression, we can collect the values at temperature, standard temperature, and the reference values. Sorry, minus HO2 gas. So at this point we should define some standard conditions and make that this Q, this is a number because we know how much heat we have to spend to keep at the same temperature and at the same temperature getting this dissociation of molecular oxygen in atomic oxygen. So we have to, we can assume here that for the species, which is the standard one, let's say the common one at standard condition, so we have that the standard condition of oxygen is molecular oxygen. We assume that our enthalpy, our reference enthalpy, is equal to the enthalpy that we have, is exactly the enthalpy that we have at this standard temperature. So this is valid for the O2. And so we have that our Q that you have to provide a standard condition to get from O2, from 1 mole of O2, 2 moles of the, so let's say this is also a molar heat that you are considering. This would be, well, it's better to write, to avoid this, sorry, because we are considering a reaction made of 1 mole of O2. We will go back in a moment to that. It's better at this time to keep it as Q. And you see that if this is 0, this is exactly this difference is the HI, only remains HF, so that we have that twice HO T0 minus twice HO reference. So we select now, we can say there is this number of moles multiplying this expression, and these two values of enthalpy. We can at this point define this reference value, and we define this reference value as such that our enthalpy, our molar enthalpy at this standard temperature, so HF such that is HO at T0 is equal to HO reference value plus the formation enthalpy at standard condition. So we introduce this quantity here to evaluate this reference value, such that if I make a substitution here, we see that our Q will be equal to twice, I replace here the value of H0 T0 with H0 reference value plus delta H of formation, this heat of formation, and we have this is exactly twice this delta HF0. This is, we define this quantity, the heat of formation, of the species of this is for 1 mole of the species atomic oxygen. This is the heat that we have to provide to form it from, let's say, this the species that make this molecule at standard conditions. So in this case, the species needed to create oxygen. It's made, we have only the atom of oxygen, so we have to start from the oxygen only. That is, we can find the standard condition as O2. So we define in this way this heat of formation, which is an important quantity for the evaluation of heat release of chemical reaction, and that can be clearly identified for each species because it refers to standard conditions and can be in some way measured. So playing with the reference values, we can say that we can define this enthalpy of formation as a reference suitable for each species. So we have that we can write also that HO2 at T0 is equal to HO2 reference plus delta HFO2 0. So this is true also for the the molecular oxygen, but in this case we have that delta HFO2 0, it's 0 because we don't have to provide it to 4 molecular oxygen, a standard condition, because it's already its standard condition. If I now consider the exothermic reaction, and we say that we start from this example, we have here that the heat of formation of carbon solid condition is 0 because it's the standard condition, and the same also here. Delta HF. And both are 0, but on the other hand, we have that to form CO2 from these two species, we have to provide a negative value of Q. So if we make this difference, we have that Q will be equal to the heat of formation of CO2. We have one mole, so here you have that more values are 1. And here, being this an exothermic reaction, we have that this Q is less than 0. So we define our enthalpy, enthalpy of formation, or heat of formation. We define it positive when we have a formation reaction where we provide energy, which is endothermic, whereas we define it as negative when we have an exothermic formation reaction. And this formation reaction starts from the values, is the reaction that allow us to form a species, a molecule, starting from its components in standard conditions. The advantage of introducing this reference for the enthalpy, so we have at this point we have that enthalpy as a fixed value that depends only on the temperature for a thermally perfect gas for each species, because we have defined that for each species we have this reference value that is such that at a standard condition its value is equal to the heat of formation. So the generic value will be clearly identified, and this helps us because we can at this point exploit the Hess law that tell us that the change of enthalpy in a chemical reaction between two different states only depend on the initial and final condition and not on the path that we have followed to reach this the final conditions from the initial one. For instance, this means that if we consider again our reaction C plus O2 that give us CO2, we can split this in a special path as the following. We have a first reaction where we form CO and O, and then we have a second reaction. So we can consider this reaction in two steps, and the heat that if we consider at constant temperature, let's say the same initial and final temperature here and here, we have the same final heat that I have to provide have to subtract to get the same final temperature in both cases. So independently of the fact that I only consider this reaction or I consider these two steps, we have the same result in terms of it that I have to subtract to keep it at constant temperature. So based on these considerations, it's convenient to introduce, as I was mentioning, our absolute enthalpy. This is absolute in the sense that we define at this point the constant that was not known before. So in general, if we are considering a single species or we have no change of composition, we can refer to a generic value of the enthalpy. We take any reference, and the only important thing are the differences. Here, to correctly evaluate the differences, we introduce an absolute enthalpy that gives us a value of enthalpy which is no longer depending on the selection of a constant value of a reference value. The reference value is defined based on this enthalpy of formation. So in general, we say that our value of enthalpy, of absolute enthalpy, H, of in general be a function for the given species, be a function of the temperature, is the one that is given by the called sensible enthalpy, Hs, plus the enthalpy of formation of that species, with the sensible enthalpy which is 0 at the standard temperature, so that we can define the sensible enthalpy. So this is the reference value, and the sensible enthalpy will be expressed as usual, but starting from the standard temperature. So a generic species I we have this expression. Now these are values that I'm now expressing as the mass-specific values rather than the molar values. Of course, we can easily change the quantities from unit mole or unit mass to the molar mass. So, of course, if you know that enthalpy of formation of a species per unit mole, we have to evaluate what is the mass of this mole, and then we can obtain the value for the unit of mass. So we have just to divide by the molar mass. So if we are considering a single species, you see that we have just differences. If I consider a generic difference of the enthalpy, say enthalpy of T1 minus enthalpy T2, our delta H. Of course, for a single species, when we have the same delta HF0, it will be equal to HST1 minus HST2, or the integral between T1 and T2 of Cp T dt, or T2 and T1. So you see that for a single species, we go back to what we already know, because we have the same reference constant. Is when we consider the mixtures where we have change of composition, that the role of enthalpy of formation becomes important. we can also say, based on the statistical thermodynamics, that it can be shown that we have to identify a given energy of the different kind of molecules at zero state, so the state at zero temperature, and for with this convenient way of treating the enthalpy, so introducing this enthalpy of formation, we take into account this this energy at zero state of different molecules. So at this point, so independently of the path we follow, we are able to go back to the heat that is generated by a given chemical reaction. Now we can also try to make a step forward and evaluate what happens at different temperature. So let's assume that we have, we like to consider now again our mixture of carbon and oxygen at a given temperature. We want that they react, and we would like to evaluate the heat corresponding to formation of CO2 that will be at a given temperature Tp. What you have to do now? We should consider that in this case we have the final enthalpy is the absolute enthalpy, so our Q will be the HF minus HI, and in this case HF will be the we have 1 mole, let's consider 1 mole of C, 1 mole of O2, and 1 mole of CO2. So we have here the molar enthalpy of CO2 that will be now the absolute enthalpy that is given by the sensible enthalpy at Tp then we have, this is CO2, and this is the value of standard condition. This is the absolute enthalpy that we have for the final product minus so we are writing it this way, and this is because delta HF0 of these two quantities is 0. So introducing the absolute enthalpy, we could imagine that this should work. So what we have to discuss it a little bit more to be sure that this is correct, and we have to exploit to this goal the Hess law, and saying that we can consider different steps to get the same final process. In general, what this law is, it's telling us that we can consider an initial condition and a final condition. They can go here in different ways. With any kind of process. it can be reversible or irreversible, but difference of the heat I have to provide to go from here to here will be equal to the change of enthalpy if I'm considering a constant pressure process, or the change of internal energy if I'm considering constant volume process. We have also said that with the S law, we can consider that if we have this initial and final state, and I have an intermediate state here, you can go from here to here, from here to here, or directly from I to F, and there will be Q1, Q2, and Q. It will be that overall heat I have to provide from I to F will be the same, independently of the fact that I go directly from I to F, from the initial to final state, or I consider an intermediate step. So this will be, in general, if I have a reaction, we are talking about reaction from initial to final condition, and if I consider, for instance, a process at given temperature, there will be the heat of reaction at that temperature from I to F will not depend on the process I follow to, for instance, evaluate this heat of reaction. So what we do in general to evaluate, let's say, the heat of reaction, and according to this, is that we start from reactants. Then the process that is, let's say, is hidden inside the expression of absolute enthalpy is that I can consider, starting from reactants, the corresponding, let's say, basic components. Let's call the species basic species, which are the components of reactants. And then we have to reach the formation of products. So this is because the formation reaction that we have talked about before are this kind of reactions. We start from basic species that are those that make products, for instance, C and O to make CO2, and we have this formation reaction. Similarly, we can consider also the formation reactions of this kind, which are the reaction to form the reactants from the basic species. So we have that these are formation reactions. And for this reaction, we know that we have some heat of formation of reactants and heat of formation of products. Of course, the species making reactants and products will be the same because actually they are related to the atoms that we have available from reactants to products. These atoms will not disappear, will be arranged in different ways. So what I can do if I would like to evaluate the heat of this reaction, of course I can consider these two steps. In this case, I have first to consider the opposite reaction here, so that I have to consider the heat of decomposition of reactants. That will be the heat of formation change of sign, because if we make, we know that if we go from here, from A to B, and then from B to A, for what we said before, we have that if I and F are the same, there is no change of total enthalpy, and so there is no heat exchange with surroundings. So this QFR must be minus Q, this heat of decomposition must be exactly the opposite of the heat of formation. And here we have exactly the heat of formation of products. So in this way, we can say that for this process, we have that the overall heat of reaction would be given by the heat of formation of products minus the heat of formation of reactants. So if this is, let's say, we are making things more or less complicated. So we say that we have initial state, final state, and intermediate state, and based on the S law, the result is independent of the step you do. And we can introduce now the basic species, and we exploit this to the formation of reactants and products to evaluate the overall heat that is exchanged by this reaction. So this heat of reaction based on the difference between the heat of formation of reactants, of products and reactants. So we are talking about heat of formation, and if we consider how we have defined it, we are considering that this is everything is happening at the standard temperature. We can make it more general and say that we should consider the basic species, basic components, as an important step that we have to take into account. And what happens if we have reactants at a given temperature TR? And you like to see what happens if we have products at a given temperature TP. It is convenient to consider here an intermediate step, which is reactants at temperature T0 standard. So we have basic components at standard temperature, and we can consider also the products at T0, so that we have a convenient intermediate step here, because here we have that there is no change of composition, so we have to bring reactants from TR to T0, and we have, let's say, this QR. Then we have here we are at standard temperature, and you can consider the above dissociation reaction that, as a consequence, has the formation it for the reactants with change of sign. Here we have at this point the formation of products, which is also something that can be evaluated based on the absolute entropy and the entropy of formation of each of the products. And at the end, we can also consider this final step to bring the products from this temperature to this other. Overall, what will be the heat exchanged in this reaction from reactants at temperature Tr to the products at temperature Tp? It will be the sum of different contributions that we have listed here. So in this way, we can evaluate how we know that this QR is a constant composition. So we can evaluate this as the difference of, I write just this, and then I will continue next time. That is tomorrow. We can consider this, how we have here the sensible entropies. The final entropies at T0. And the initial one is at Tr. And what will be the next step? Of course, will be the QFR is the heat of formation of reactants. We have to consider the mole of reactants that we have available, and the molar heat of formation of each species. We know that this QFR is given by this expression. Similarly for the products. So we can stop here for today, and we will continue tomorrow this discussion.
Arrivederci.
Arrivederci.